At number 8, we're finding the voltage reading across the voltmeter. So we have X is equal to 8.8 in this particular problem. So what we're going to have to do is we're going to have to find the equivalent resistance, then we're going to have to use Kirchhoff's rules, and then solve. Okay, so let's find this equivalent resistance first, and then we'll redraw the circuit, and then use Kirchhoff's rules. Okay, so the equivalent resistance of the 1 mega ohm and the 83 kilo ohms is like so. So 1 over R equivalent is going to be equal to 1 over 83 kilo plus 1 over 1 mega. Okay, so 83 kili, that's going to be 83,000, and then 1 mega is 1 million. So let's find the R equivalent. So I get an R equivalent of 76,639. Okay, so now we can redraw our diagram. So this time, we're going to replace those two resistors with the equivalent resistance. Oh, one thing I forgot here. Let's go ahead and add this one to it, the 16 kilo ohms. So plus 16,000. So that's going to give us 82,639. Okay. So let's put that resistor in here. Not pretty, but it'll work. There's our battery, which is going to be 8.8. And then over here, we got to put this one in here. So the only thing that's changed here is this value, and that's 82,639 ohms. Alright, so that's our new value over here, our equivalent resistance, and our I1 is still going to be the same direction. Our I2 is going to still be the same direction. And I3 is still the same direction. Alright, so let's write out our equations. So let's start with the junction rules. So I1 comes in here to this junction. So we have I1, and then I2 is going this way. Minus I2 minus I3 is going to be equal to 0. And then we want to put in our loops. Okay, so remember, V is equal to R. Okay, so we'll start with this loop over here. We have 8.8 volts going this way. So this is our positive. Alright, so 8.8 plus IR here, so alright, so here we're going to have R1 35 times I1, and actually that should be negative because the voltage is decreasing as we go across the resistor. And then we're going to subtract this resistance times this current. So 1.4 kiloohms, we'll call it 1400 times I2. And of course that's equal to 0 when it gets back around to the battery. Okay, so now if we follow the current this way, it's going to be negative. If we go the other direction across the current, it's going to be positive. Okay, so we want to designate a loop, or direction for our loop, since we have two arrows here, so we'll go this way. So voltage will drop across I2. So we have I2 1.4, so we don't have voltage given on this one. It's over on this other side. It's not part of the loop, but that's okay. We can make it work. So let's go I2, 1.4 kiloohms times I2, so 1400. I2, and then we're going backwards against this one. So I've got this should be a minus, this should be a plus. So 82,639 times I3. And that's going to equal 0. Alright, so there we've got our junction equation and our loop equations. We can set those up in a matrix and then solve. So 1, -1, -1, and then we're going to have -35, -1400, zero. Of course, we gotta have the 0 over here. And this one's going to be 8.8. On the bottom here, we've got I2 and I3. I1 is going to be 0. I2 again is negative 1400. And then 82, we'll just call it 83,000 just for short here because everything's all crowded. And that's equal to 0. So now we're going to put it into a matrix calculator. Alright, so here's our solution. We have I3 is equal to 4.13 times 10 to the negative fifth. I3 is really the only one we care about because we're looking for the voltage across the voltmeter. Okay, so I'm going to go ahead and write that down, and then we'll work on solving for that voltage. Okay, so now we have our current. And current is going to be the same through this resistor and through these parallel resistors. Okay, so we're not too concerned about this one because since it's in parallel. However, it will affect our voltage drop. So we should probably go ahead and calculate our voltage drop across the 16 kilo ohm. But I think we can do it with just
I'm not sure
with just these two as equivalent resistors. So let's approach it from that perspective. See how things come out. Alright, so here's our current, 4.13 times 10 to the negative fifth amps. Our equivalent resistance is going to be this 76,639. We know that V is equal to IR. Both of these are going to see the same voltage. So let's go ahead and multiply these together. So our voltage is going to be equal to 4.13 times 10 to the negative fifth times 76,639. Alright, so let's calculate that. Alright, so 4,000, let's see, what's to the negative third? I'll just write it in there in scientific notation. So 4.13. Let's see, where is it? Alright, 4.13 times 10 to the negative 5, and then we're going to multiply that times 76,639, and we get a voltage of 3.17. Alright, so let's recap. We find the current on I3 using Kirchhoff's loop rules. Once we find that, we know that with the equivalent resistance, we're going to have the same voltage across both of these circuit elements. We use V is equal to IR, and we find the voltage drop across the resistive element, which is 3.17 volts. Alright, so I've solved this problem, and I took a look at it, at the solution, and my answer does not agree with the solution. Surprise, surprise. However, I've scrutinized everything with a fine-tooth comb here, and my answer is correct. So I feel very confident that the answers on the Connect site are probably in error. Okay, I even matched my numbers up with theirs line for line in their equations. So anyway, make sure you work it out like this. Use Kirchhoff's rules. Find that current, and then use the current and the voltage, or the current and the resistance, and find the voltage. Ohm's law is very straightforward, and that'll give us a legitimate voltage drop across that circuit. So with all that said, if you follow these steps and you still end up with an incorrect answer, just shoot me an email and I'll check it by hand. Thanks.